Okay, so okay, V1, V2 is 1, 4, 5, 3. So I'm going to say V2 norm, and I'm going to call that U2. Okay, V2 norm just equals the vector. Now I'm going to put it in column form. 5 over the square root of 34. Three over the square root of 34, because the magnitude of this, 5 squared is 25, 3 squared is 9. Add them up, you get 34. And the magnitudes and then the square root, Pythagorean theorem, that I'm not even going to justify anymore. There it is. Okay? Then, projection of V1, projection onto, and I'm not going to call it V2 norm, I'm going to call it U2 now. So projection onto U2 of V1 equals V1 dot U2 over magnitude of U2 multiplied by U2 over magnitude of U2. But remember, U2 is normalized, so its magnitude is 1. So that's just V1 dot U2 multiplied by U2. Projecting V1 onto U2 is particularly simple if U2 is already a unit vector. Okay, there's a projection. Now we're going to let U1 be what we would have formerly called V1 perpendicular. It's V1 minus the projection of V1 onto U2, which is, write it down here, V1 minus V1 dot U2, U2, and now we can just take our coordinates and calculate it. Okay, so it's, go back to columns, 1, 4 minus 1, 4 well, we've done the notation, and the reason I'm using columns is so I can put this in the standard matrix form. So let's do the dot product the way I intended. It's going to be minus 1, 4 multiplied by 5 over the square root of 34 3 over the square root of 34 times the 5 over square root of 34, 3 over the square root of 34. And that's not written very clearly but we understand this vector is the same as this, it's just your u2. And now we can do the arithmetic. You got 5 over the square root of 34 and 12 over the square root of 34, which is 17 over the square root of 34 times 5 and 3 over the square root of 34. And it's just simple calculation from now on. Notice that you have square roots of 34 here, so that square root isn't going to bother you. You don't ever really need to calculate it because you're always going to be multiplying it by itself. So we're going to have 17 times 5, which is 85, over 34. And 17 times 3 is 51, that's over 34. And not only that, it gets a little better. 85 over 34 comes down to 5 halves, or 5 halves. And 51 over 34 is just 3 halves. And often you'll get that sort of handy simplification, especially in early steps. 5 halves, not 3 halves. Jumping the gun. Try to erase this as neatly as possible, because Zoom also, not Zoom, but Zoom combined with my internet provider tends to blur erasures very badly. And it could have been a better 3. Let's see if we can repair that. Okay. So that's what? That's negative 3 halves. And that's 4 minus 3 halves, which is 8 halves minus 3 halves. So that's going to be 5 halves. Okay. That's going to be our u1 vector. And now we have an orthonormal basis, I hope. Let's see. So, u1, u2 equals negative 3 halves, 5 halves, and actually I'm one step shy of orthonormal. And then we have 5 over the square root of 34, 3 over the square root of 34. Now that's clearly orthogonal. Okay, just in case you can't see it, but clearly orthogonal because the dot product here is obviously 0. You get negative 15, and then it's over 2 times the square root of 34, and plus 15 divided by 2 times the square root of 34. Gives you 0. This is orthogonal, it's not orthonormal. Okay? To get it orthonormal, you're going to have to normalize this vector. So, it's orthogonal, almost orthonormal. So one more step to orthonormalize it. Well, that's the basis for just what you have with 2 vectors. Let's consider now what you have, or what you have to do if you've got 3 vectors, say, that form a basis. So that would be, for example, 3 vectors in R3. And we'll formalize the process just a little more.